This subject is like many other subjects in that you have to crawl before you can walk, and you have to walk before you can run. So we're working our way through a series of increasingly complex examples, and we're still working on the first bullet here, where we're trying to make sure that we understand how to read the graph of a given polynomial. Then we're going to take a different tack, and we're going to start analyzing the algebraic forms of given polynomials. But first, we want to do a couple more of the graphing problems, just to make sure that there's no confusion with that. Here's the next example. And if you're feeling confident, you could certainly stop the video here and try to work this out for yourself, see how far you can get, see if you match. But this is pretty similar to prior examples, except that it's a bit more complicated. So let's take a look at what we've been given here. We've been given a polynomial. It looks like it's an even degree because of the end behavior. So in other words, the degree, it can't be a quadratic, but it could be a fourth degree, or it could be a higher degree. We're going to assume the minimum necessary degree as usual. Now, when you look at the scale on the two axes, you notice that they're using a different scale. So on the x-axis, each of those hash marks is 1 unit, meaning that right there, that's a root at x is -1. And it looks like it has even multiplicity because the graph bounces off the axis, as we discussed in a prior video. I have another root right there, and that looks like it's at x is +1. That's got odd multiplicity because the graph just punches through the axis. And then I have another one right there, and that is at x is 4, and that also has odd multiplicity. And so if you consider that the minimum reasonable, or the minimum necessary multiplicity for the root at -1 could be 2, and then the multiplicity for the other roots could be 1 at minimum, you're looking at, again, a minimum of a fourth degree polynomial here. And the one other thing that we would mention is that we have an additional piece of information. We are supposed to make sure that this polynomial maps x equals 3 to y equals 8. Now, as far as the end behavior is concerned, you can see, because both ends of the polynomial are running off to -infinity, it looks like we probably have a leading coefficient here, which is negative. In fact, it's a given. We have that. So if we're working smart instead of working hard, we're going to allow for that from the beginning, and then we'll figure it out what it needs to be in order to achieve this when we get to the calculator. So I've got p of x. And a is going to be my unknown leading coefficient. For the root at -1, I'm going to have x plus 1. And we were saying that assuming the minimum necessary degree, it's going to be squared. It's going to have a multiplicity of 2. For the root at 1, I'm going to have x minus 1. And for the root at 4, I'm going to have x minus 4. So what I want to do is start to expand this. When you square out x plus 1 quantity squared, you get x squared plus 2x plus 1. And when you multiply x minus 1 times x minus 4, you get x squared minus 5x plus 4. And now I need to continue expanding. I'm not going to bring a into the mix until I need to. X squared times x squared would be x to the 4th. X squared times -5x would be minus 5x cubed. X squared times 4 would be 4x squared. And then 2x times x squared would be 2x cubed. And it looks like I'm going to have to break a line here. 2x times -5x would be minus 10x squared. 2x times 4 would be 8x. And then 1 times x squared would be x squared. 1 times -5x is -5x. And 1 times 4 is 4. And so I'll collect my terms. I only have the 1x to the 4th term. I have a -5x cubed and a positive 2x cubed. That's going to be minus 3x cubed. For second degree terms, I have a 4, a -10, and a positive 1, so that's going to give me -5x squared. For the first degree terms, I have 8x and minus 5x, that's 3x. And then I have a 4. Okay. Now, we want to make sure that we are working efficiently here. And what I'm looking for is I'm trying to find the value of a. And so let me show you a slick way to make your calculator do that for you. Let's switch to the calculator here. You're going to have to key this in, but instead of working, well, I prefer to work smart whenever I have the presence of mind to do that. It's not very often, but anyway, check this out. Let me quit this for a second. You know, your calculator has a bunch of memory registers, and these are in green. You can see if you hit the alpha key and you hit any one of these keys down here, you're going to get the memory register that appears in green above it. So like alpha A is currently minus 0.5. Alpha B is some value, you know. And so I use these memory registers, and I have these values in them. I don't know where they come from. I can't remember anymore. But anyway, I'm going to store 1 in A, because I'm going to be using A as part of my key in, like this. And by the way, you can see now that A has 1 in it, right? You know, I forgot to execute it, actually. So yeah, check it out. There you go. All right, so I go back to y equals, and I'm going to put in alpha A times the quantity, and then I'm going to type in that polynomial just like I had it on the iPad screen. So I have x to the 4th. I got minus 3x cubed. I have minus 5x squared plus 3x plus 4. And then I'll close that. And if I quit this and I standard zoom it, graph looks like that. Now that does not look very much like what we saw before. That's not the graph that we were working off of. The end behavior is wrong, and for sure it is not going to map 3 to 8 like it's supposed to. You can check it out. I can go here and I can say put in a value, and if I put in 3, you can see that it's currently mapping 3 to negative 32. So my choice for A boils down to this. I'm effectively asking myself, hey, what do I need to multiply negative 32 by in order to make positive 8? And obviously the answer would be minus 1/4. And so that's the value I'm going to put in for A. I'll get out of here, and I'm going to say minus 0.25. That's the decimal version of 1/4. I'm going to store that in alpha A. And now when I go back to graph that, notice that the graph looks very much like what we were working off of. Now, if you want to make it more convincing, you know, you can notice, okay, so the scale here is a little different. It goes negative 6 to 6, 10 to 14. Okay, so I'll do the same thing. So negative 6 to 6. Scale of 1 is fine. Negative 10 to 14. And if you want, you just do the same thing. Scale of 2. It doesn't really matter. Here's the graph. And we want to verify that it maps correctly the value of A, or the value of 3. We want it to map to 8. That's what the graph we were working off of said, remember? We're supposed to get 3 to map to 8. So that's what I'm going to do. I'll go second trace, and I'll put in a value. And sure enough, it comes out at 8, just like we wanted. So at this point, I know what I need for my final answer. I know that the value of A has to be negative 1/4. And I don't want to say equals because that is silly. Via calculator. So, what's my final answer going to be? Well, I hate to, well, I'll just write it a couple of times. So, the first version of the answer is just going to replace the A as you see it up there. So, P of x is minus 1/4 times the quantity x to the 4th minus 3x cubed minus 5x squared plus 3x plus 4. But I don't know that your learning management system would accept it in that form. You know, usually they're pretty rigid about those kinds of things. So equivalently, if I expand that, I'm going to have as follows. I'm just distributing the negative 1/4. So I'm going to have minus 1/4 of x to the 4th. I will have positive 3/4 x cubed. I will have positive 5/4 x squared. I will have minus 3/4 of x. And then minus 1/4 times 4 would be minus 1. And so I'm going to assume that that's probably what they would want in the learning management system. I could be wrong about that, but I'm thinking that that's it. Let's see what we have next. This one's a little bit more demanding for obvious reasons. So just eyeballing the graph, what's the scale that we have here? Well, it looks like on the y-axis, they're using a scale of 3 units per hash mark. On the x-axis, it looks like they're using a total of 2 units per hash mark. So you want to make sure you're reading those roots correctly. And here is what I see. It looks like I have a root right here at negative 3. And because of the behavior of that, it looks like it has odd multiplicity. I have another root, and that looks to be at x is 1. Negative 1. Also odd multiplicity. I have another root right there that's at x is 0. That's even, because the graph bounces off the x-axis. And then I have another root right there at x is 2, and that's odd. So what's the minimum necessary degree in order to get a polynomial that looks like that? Well, I have the one which has a minimum degree of 2, and then I have 3 others that have a minimum degree of 1. So it looks like the minimum degree would be 5. Now, as far as the end behavior is concerned, the end behavior is consistent with a 5th degree polynomial that has a positive leading coefficient. It's going off to positive infinity on the positive x side. It's going off to negative infinity on the negative x side. And so I'm still going to allow for the possibility that there may be some leading coefficient, a positive number, because I'm still trying to map negative 2 to positive 16, and I'm not going to know whether or not I have that until I get it graphed. So here's where we're starting. And again, feel free if you want, pause the video, see if you can match on this. P of x would be as follows. The root at negative 3, I'm going to give that, I'll put my leading coefficient in, and then I'm going to have x plus 3, and that's going to be to the first power. I have a root at x is minus 1, that's going to be x plus 1, first power. I have a root at 0, and that's going to be x minus 0, quantity squared, because again, it's a clearly even multiplicity. And then I have a root at 2, and that's going to be x minus 2, first power. Now, multiplication is a commutative and associative operation, so I'm going to tidy this up a little bit here before I start to expand. I'm going to have the a out there, and as far as the x minus 0 quantity squared, that's the same as x squared, right? So I'm going to put that out there. And then I have x plus 3, x plus 1, and x minus 2. And usually when I'm expanding this kind of a thing, I'm going to be multiplying binomial against binomial, or binomial against something else, or whatever I need to do. Here I think it's going to be easier if I distribute the x squared over x plus 3, and then I multiply the x plus 1 and the x minus 2 together. That's just what I chose to do. You could do it differently, you'd probably get the same result. So I'm going to have a times the quantity. X squared times x is x cubed, and then x squared times 3 is 3x squared. And then x plus 1 times x minus 2, that's going to be x squared minus x minus 2. And if I continue to expand, I'm going to have as follows. X cubed times x squared is x to the fifth. X cubed times minus x is minus x to the fourth power. X cubed times minus 2 is minus 2x cubed. 3x squared times x squared would be 3x to the fourth power. 3x squared times minus x would be minus 3x cubed. And I think I'm going to need to break the line here. 3x squared times, no I don't. 3x squared times negative 2 is negative 6x squared. I'm good. Let's collect our like terms here. So I have the 1x to the fifth term. I have a negative x to the fourth and a 3x to the fourth. That's going to give me 2x to the fourth. I have a negative 2x cubed and a negative 3x cubed. That's going to be minus 5x cubed. And then I have a negative 6x squared. So now I'm ready to find out the value of a. So I'll do the same trick over here. I probably would want to quit this. I want to start with a being 1, because if I start with something else, it makes it confusing. So I'll put 1 in there, and then I'll go back to y equals, and I'll just clear all that out. So I'm going to have a times a quantity, and then my polynomial is x to the fifth plus 2x to the fourth minus 5x cubed minus 6x squared. Whoops. I don't want an exponent on that. I want it on that. And then I need a closer. So let's graph it in a standard zoom and see how it looks. Okay. Now my original graph that I was working off of, a little different scale there, as you can see, goes like from negative 3 to 3 and then negative 15 to 21. So let's mimic that. Negative 3 to 3, scale of 1, and then negative 15 to 21, and it was the scale of 3. Here's the graph. Okay. Well, proof's in the pudding. So the main thing that we're interested in is we want to see whether or not it's going to map, negative 2 to positive 16. And it looks like it does. And so what that means, practically speaking, is that we just found that we don't need to have, we can use 1 for a. Let's put it that way. That's what we found. Because it maps already as we want it to map, and so we don't need to change that. So I'll come back here, and I'll say via calculator, so my final answer would be that p of x is x to the fifth plus 2x to the fourth minus 5x cubed minus 6x squared. Pretty straightforward. Stay tuned for the next video.